What I'm going to show you here is I'm going to talk to you about how Gaussian elimination can be applied on 4x4 systems of matrices as well, just to develop on the 3x3 systems that we've been using up to this point. So I'm just going to show you an example of this, just to prove that it doesn't matter how big the system of equations we've got is, we can apply Gaussian elimination and our elementary row operations such that we're able to solve any system of equations quickly, easily and efficiently, rather than having to take each system and each equation, modify each equation to change it to the subject of one letter, substitute these all into an original equation, work it through, and then do back substitution into each of them with the new variables such that we can find the original. So a lot of work like that. Gaussian elimination just makes our life a heck of a lot easier. So let's imagine I want to solve this system of equations here for the variables w, x, y and z. Now, like every other system of equations when we've come to solve it with Gaussian elimination, the first thing we have to do is set up our augmented matrix, and then we want to put it into upper triangular form. So if I set up my augmented matrix, I've got 1, 1, 1, 1 and 5. I've got 2, 3, 1, 2 and 9. I've got 1, negative 1, negative 1, 3 and 1. And I've got 2, negative 1, 2, negative 1 and 4. So there we go, we've set up our augmented matrix. Now, similar to what we did before, we want to put it in upper triangular form. Now that we've got 4 equations though, and it's a 4x4 system, upper triangular form is no longer just these bottom 3. Upper triangular form is actually getting this entire triangle here with zeros in it. So it's no longer just one little triangle with 3 zeros, it's now got 6. But the steps are the same. We still use the same set of elementary row operations and the same methodology to do this, it's just we'll have to do a little bit more. So let's begin the process. We'll start by doing row 2, take away 2 row 1. We'll then do row 3, take away row 1. And we'll do row 4, take away 2 of row 1. Doing that, that will change my matrix. I'll still have the same first line, so I'll still have 1, 1, 1, 1 and 5. My second line becomes that, take away 2 at the top. So I'll get a 0, 1, I'll then have 1, take away 2, so negative 1, 2, take away 2 of those, so 0, 9, take away 2 of those, negative 1. My next row, row 3, would be this take away that top row, so I'll end up getting 0, negative 2, and have negative 1, take away 1 again, so I'll have negative 2 there as well. 3 take away 1 gives me 2, and then 1 take away 5 gives me negative 4. And my bottom row is just this row, take away 2 of the top row again. So I've got 0, I'll have negative 3, I'll then have 2, take away 2 of those, so I'll have 0, I'll then have negative 1, take away 2 of those, so I'll have negative 3, and then 4, take away 10, gives me negative 6. So I've changed it into that form now. Next, I'm looking to eliminate the numerical values in this part of the matrix here. So again, I can do my elementary row operations in order to do that. So what I'm going to do is I'm going to take row 3 and I'm going to add on 2 of row 2's, and I'm going to take row 4 and I'm going to add on 3 row 2's. What that'll do is, again, it will change my matrix. So my top line will remain the exact same, 1, 1, 1, 1, 5. My second line, that will remain the same now. So I've got 0, 1, negative 1, 0, and negative 1. My third row now becomes this row plus 2 of the second. So I'll still have a 0 there. Negative 2 plus 2 gives me a 0 for my next entry. I then got negative 2 plus 2 of the negative 1s, so I'll end up with negative 4. 2 plus 2 zeros, well, that's just 2. And then negative 4 plus 2 negative 1s gives me negative 6. Then my bottom row comes into play, so I'll get 0. This next entry, because I'm adding on 3 of these, that will again become 0 as well. I've then got 0 plus negative 3. So I'll end up getting negative 3 there. I'll end up with negative 3 plus 0. So I'll get negative 3 there for that one. And then look at this last one here. I'll have negative 6 plus 3 of the negative ones, which will give me negative 9. So what I now have is a system of equations that look like that. Now these last two rows, if you'll notice, what I could do, row 3, I could make row 3 the equivalent of a half of row 3 just to try and whittle down the values. And I could make row 4 the equivalent of a third of row 4. And what I'm then going to do is swap the two of them around. Because if I take a third of row 4, this becomes negative 1. And if I then take this and switch it here, what that means is I can use the negative 1, scale it up appropriately, and get rid of the value from this that will now be in the bottom row. Because if I take half of this, I'll get negative 2, and I'll have a negative 1 there. Well, it's easier to scale negative 1 up to be negative 2 than to go back the way and do negative 2 divided by 2 to get to the negative 1, and then have to have fractions working within my system. So I'm going to do that as my next step. So what that then allows me to do is once I've done that and I've done my swap, I'll have my top row being the same, 1, 1, 1, 1, and 5. My second row, again, that will still be the same. So I'll end up with 0, 1, negative 1, 0, negative 1. My third row, that will then become 0, 0, negative 1, negative 1, negative 3. And my bottom row will then become 0, 0, negative 2, 1, negative 3. So now that I've got that and I'm set up, what I can do is if I take row 4 and I take away 2 of row 3, that'll end up giving me slightly easier numbers to work with because I won't have fractions in it. If you kept it the same as before and you did have fractions within it, you'd still be perfectly fine. You'd still manage to get a final solution. All that you would find is you'd have to do a bit of work with fractions, and I just want to make my life as easy as possible, to be honest. So I've got 1, 1, 1, 1, 5 is my top, 0, 1, negative 1, 0, negative 1 is the second, 0, 0, negative 1, negative 1, negative 3 is my third, and then my bottom row becomes 0, 0, negative 2 minus minus 2, so that becomes 0. I've then got 1 minus minus 2, so that becomes 1. And I've got negative 3 minus 2 times negative 3. So 2 times negative 3 is negative 6. I've then got negative 3 minus minus 6, so negative 3 plus 6. That gives me 3. So there is my matrix now. So what I now have to do is I can then read off the solution to my system of equations using these answers and just remembering what each of the columns represents within my system. Just remember, first column, this one here, that's your W, second your X, third your Y, last one's your Z. So reading it off, I can say from the bottom row that Z is equal to 3. Second row here, I know that minus Y is minus Z, so minus Y minus 3 is equal to negative 3. So negative Y is 0, so Y is 0. This line here tells me that I've got X. It's then minus Y. Well, if Y is 0, it's just X. That equals negative 1. And then for the top row, what I'll end up getting is W plus X, so plus negative 1, plus Y, so plus 0, then plus Z, so plus 3, is equal to 5. So I know that W plus 2 is equal to 5. w is equal to 3. So for this system of equations, what I know is that w is 3, x is negative 1, y is 0, and z is 3, gives me the solution that satisfies the entire system that we've got. Working with the 4x4 matrices, none of the steps change, none of the theory changes, it's just we've got a little bit more work to do, and really the big change is our upper triangular form is just slightly bigger because it's now all of this that we want zeros rather than just the bottom 3. So don't be put off and don't be intimidated when it's a 4x4 system, or even more. All of the theory and all of the material and all of the work we've done up to this point is still applicable, it still works, and it's still something that we're able to do. We just have to maybe do a couple more lines and have to possibly deal with a couple of extra letters along the way.